All right, good morning. I posted some things, announcement yesterday. I hope you all get them through B-Course. I don't use B-Courses for much, but I use them for announcements and uploading these old exams as well. Next week, next Tuesday, we'll have a review. And then I'll, hopefully we'll go through everything. But just so you know, for now, I think the big decision here is that today, hopefully if I manage to cover all of 4A, that will be covered on the exam next week. And you will, of course, have a homework due on Tuesday and a programming assignment too, and all of that will be covered. Okay? And I'd like to post solutions, and I've posted solutions to programming assignment 1. I didn't find a good spot to put them, so I put them right here next to the PDFs, right? And next Tuesday at 6 o'clock, right after your sections, I will post it for 2 as well, so you can quickly at least have a day or 1.5 to check your own solutions. But of course, the right way to do this is to make sure your programming assignment is good in the first place. Just come and show us and help. You can make it perfect if you just spend some time on it. And homework and material is otherwise, as I said. Let's see, what else did I say here? You know all the deal with it's a closed book exam. Frequently asked question is what you need to know. And you who come to classes, you know what I think is important. Basically, all the chapters of the book are covered. But you know that, for example, I said all these messy expressions with splines. I kind of trivialized and did my other solution with a big linear system. So I do things in slightly different ways that are probably easier to remember. Miller's method, all those messy expressions. I'm not saying you wouldn't benefit from remembering it, but the thing we emphasize is really exactly what the method is doing. And you will get a good impression, I think, from all the old exams that are posted. Lots of them that are, I would say, very similar, although the material might differ a little bit. Some of these gave 2 midterms. Here we have just 1 in the middle of those 2, so some things you don't even know about. I did a big warnings here. They might be different length of exams, etc., right? But go through them. I think it's excellent. Of course, the most relevant one for you might be the one I gave last year, or last fall. Okay? So that's good practice material. But all of these are using, I think they all use the same book. This book has been used a lot for this course. There are solutions to some of them. I just warn you that I don't take responsibility for other people's solutions. In particular, I found a mistake on one of them. And if you really want to spend time, there are quite a few posted on our math department exam archive. The reason I picked out a few particular ones was that they matched our material well and they used the same book. But if you want to, you could go here and look at other ones, but they might be quite different. I picked all the ones that I think you will benefit from the most. So where did it go? Plenty of preparation material. We will do. I will do review here next Tuesday, of course, in class. Just nothing special. Just going through everything and showing some extra examples, and hopefully that should be it, right? Any questions about the exam? Administrative or on the material? Yeah. What? A blue book? No, I'll do it such that you have space below each problem to write on. Just bring the stuff I said. Pens, pencils, and erasers. Yeah. I have not decided on many problems. And it's kind of iffy because sometimes I do A, B, C, etc. And then, I do fewer problems because of that. So it's hard to say. But you'll get a good impression from the old ones. I'd like midterms to, I don't like when they are too stressful, but midterms end up being more stressful than finals. So, don't get stuck for 20 minutes on one problem. Then you got to leave it, and you got to have some tactics. Unfortunately, that's how midterms work out, because it's such short time. And this room seems a little tight. So I'm going to do some, I think I'm going to have to make some, it's actually 199 seats, I think, in here. And there are, including concurrent enrollment, there's more than 200 people enrolled. It's kind of a problem. But I'll make some arrangements and let you know. But most of you are going to take the exam here for sure. All right? How's it going with the programming assignment 2, by the way? You're getting the results out? You realize that last week we covered integrals, and you should be able to do problem 3 as well. And it's short when you get it right, but I'm not saying it's easy. It's a pretty good programming assignment, I think. It tests a lot of stuff. Using the splines for a non-trivial problem, Newton, and then integration, right? So, And these are actually quite relevant things. You know CAD, I told you about CAD, like when people draw for computer graphics, they want to do all these things. They have a curve or shape. They want to find where it intersects certain other lines and shapes. They want to compute the length, etc. It's a typical stuff that show up. So these problems are not that made up. Well, of course, the examples are made up. Anyway, let's see where we are. I'm going to first review a little bit of the composite rules. This is extremely important. Why? Because I said the Newton codes are just not practical. If you want to do a complex long integral, like your spline, for example, it's a little, you might get away with your spline, because it's just, what, 6 point or something, right? But it's, in general, what if you have 100 points? You don't want to put a 99th degree polynomial through it, although you could, in principle. It would be messy, and I did show you this effect that polynomials like to do this after a while. So you don't want to go too high degree. Similar to splines for the interpolation, we'd instead do composite. You just split it up, and you do piecewise something. And the simplest is, of course, piecewise straight lines, which is the composite trapezoid. And I drew figures last time. But it's probably maybe the first thing you would think of almost, if nobody told you anything. You want to estimate. I give you points, and you want to estimate the area under the graph. Draw straight lines. That is the area, right? Well, we have a nice error formula here. I tell you that these error formulas are important in so many ways. They tell you what it's exact for, namely the degree of precision. What is the degree of precision of that first method? It's 1, because it's exact for straight lines. But if you put a quadratic in there, you get a non-zero second derivative, and it's not exact any longer. Okay? Degree of precision is a very simple concept. This formula is exact for constants and straight lines. Not too interesting, because if you know you have a straight line, you wouldn't use the formula in the first place. You would just integrate it, right? But it turns out to be practical, because any function can be expanded at Taylor. So it tells you a little bit about the accuracy here, which terms it kills off. The h square is also important. It tells you approximately how much better it gets if you divide by 2, or 10, or anything. But maybe second order is not enough. So Simpson's rule we talked about. These 2s and 4s, don't mess it up. It's kind of easy. We did a bunch of examples. Just learn that pattern, right? And even learn how to derive it. If you have a Simpson's rule said 1, 4, 1 times h thirds, right? Now if you put another one next to it, of course it's going to be 1, 4, 1 plus 1, right? So it's 1, 4, 2, 4, 1. And to put 100 next to each other, it's going to be 1, 4, 2, 4, 2, 4, 2, and at the end it's 4, 1. That's how we use this formula. It's very practical. We use it a lot. And it's, of course, much more accurate than in general, if h is small enough. Then we talked about Romberg. Here's just a different idea. Why don't we just stick with the trapezoidal rule, which we understand, and then we start doing it for successively finer intervals. And we realize that this is exactly what Richardson extrapolation likes. So if you like, if you have an error term of this form, in fact, you need even more. And I told you it can be shown that for trapezoidal method, there's this constant here times h squared, right? That's what it says here. But you can also say that it's plus another constant times h4 and nothing h3. Okay? So it fits this second part of Richardson extrapolation where you have the even terms. Then you might say, hey, let's not worry about Simpson. Let's just do, let's say, just 2 trapezoidal rules where you divide h by 2. Okay? Then you can just apply one step of Richardson, and you get a method that I think your homework said was actually equal to Simpson. So that's another way to do Simpson. But even more so, you can keep on going. So you can do like 4 levels of composite trapezoid, like one big h half plus h half, and split it into that. You do a bunch of trapezoidal rules, and you applied Richardson. Excellent method. One thing that makes it even better is that you can actually compute all these nested ones efficiently using this formula here. And I talked about it last time. If you do one trapezoid, and then later on you want to do another, you realize you don't have to recompute the endpoints, FA and FB. You just have to add in the midpoint with appropriate weights. So it's no magic. And if you now want to split again, you can reuse those 3 points and just do 2 more. So you can do it very efficiently, and that's a nice method. Here's an example for how it works out. All these R1, R2, R3, RK, they are all trapezoidal methods. I have not done Richardson yet. This is just a way to efficiently do trapezoid. The first one is obviously just trapezoidal method with the endpoints, right? So that's not too sophisticated. And the next one, you see again how we can reuse the previous one and just add in another one. And we keep on doing that according to this formula. And as soon as the general sum notation shows up, maybe people get lost. Don't get lost. It's pretty easy if you just look at it visually. And then the next step was, hey, let's now start playing with this column here and apply Richardson extrapolation, just like before. And we did some demos showing that this is can be extremely accurate. Of course, the 4 here, because there were even powers. When you do the Richardsons, you'll see, I think some of the old exams are showing you how to do, and even the homework sometimes, that you Richardson on things that are not maybe fitting this pattern. But typically, it's either you have all the terms, like h, h squared, h3. That's the regular Richardson. And I think then you divide by 2 to the j minus 1, right? But then we said if you only have even, it became a 4. And you can, if you forget that, it's kind of easy to derive. It's just elimination. But you can remember those two. But Richardson is really nothing but writing out the whole expression, including the h2, h4, whatever terms you have, and eliminating when you have two different h's. It was really just a few lines to derive Richardson, so don't let that confuse you too much. I did go through this MATLAB code, also emphasizing that if you don't like this compact notation, don't freak out. But you're starting to get used to MATLAB now. I think this entire code, maybe except for this line, should be really quite straightforward for you guys. There's a big array R. There are two loops, of course, because I'm trying to fill in a matrix. So one loop is over the refinement in the trapezoid, and the other loop, the J here, is the Richardson's various levels. So please look through this code and see if you understand it. That's basically what we did with the composite stuff. And the goal now is going to be to talk about adaptive quadrature. I think I convinced you last time that if you have a function that is doing very, very little, there's the issue of choosing h, right? And you noticed in your homework, what should you select h? And it seems like the finer, the better. But there's a level when you don't want to do too fine because it's a lot of work. What if you have a function that is smooth and nice and then something insanely sharp? And you can, from physics or whatever, you can make up whatever you want. And I mentioned like some nuclear reactor that is not doing anything, and then within microseconds it starts doing crazy things. How do you integrate a function like that? It's probably a bad example, but the idea is that maybe you can use huge h's for most of the time, and then you get to zoom in at some other time. And it's actually quite straightforward to do. You just choose different h's. These formula all assume, like for example this Simpson, the 1, 2, the 1, 4, 2, 4, 2. They all assume one and only one h. All these points are equidistant, right? So you got to change the formula, but it's obvious how to do it. It's really just an integral can be split up in various intervals, and you just change the h at one of those intervals. We don't even write down the general formula for that, but it's easy. You can, if you decide that here's a little chunk of your interval that you want to refine with another h, you just take it out and run another h on that interval. So that's the easy part. The difficult part is how do you decide what h you want? And all your exercises are a little misleading because you usually play with this error term, right? A typical exercise for you guys is to estimate the error or bound the error. And I like to emphasize that's rigorous, but maybe not so practical. It's rigorous in the sense that it's a proof. You're really guaranteeing that this bound is met. Why is it not practical? Well, the main reason is that the f2 derivatives here is not known. It could be, but it's often not practical. The other reason it's not practical is that sometimes these bounds end up being way too pessimistic. They are magnitudes more than the actual error. So, they are what they are. It's kind of nice as mathematicians to be able to say that, look, we know, we can prove that the error is small enough. But in practice, you might want something else. So that's what we're going to look at now, something that is used much more in practice for error estimation. And it's, so the field is called error estimation, as opposed to, I would say, maybe error bounding. Well, kind of the same thing. We want to estimate the error. Here's the trick. Here's a very neat trick. And it reminds of everything you've done, Richardson and all, and composite trapezoidal rules. But the trick is to run things with different h's. When you do that and know something about the error, you can start solving for things. I'll show you. It's actually quite straightforward. So you want to compute an integral of f of x from a to b. Okay? And you know that you can use this using Simpson's method with only one chunk. And I'm going to call that s parentheses a comma b, just for notation. Okay? So this, of course, means h thirds times f of the left endpoint plus 4 times the midpoint plus the right endpoint, right? But that's what we call s of a comma b. What I want to emphasize is the error term, which we derived back then. And it had this h5. There's a fourth derivative of f for some mu. It has an error term that we knew before. Okay? If nothing else, you kind of just like to compute s and estimate that. But that's not so easy. So if you do have information about the fourth derivative of f, you can do it. And that's the typical exercise you've been doing so far. But let's say you don't know this. What can you do instead? The trick then is to say, why don't we just do another Simpson? And when I say another, I mean a different h. I just want to change the h here. So integral from a to b of f of x is, of course, also equal to Simpson going just halfway, plus Simpson from the middle to the right, right? So now I split up Simpson. Actually, in terms of points, I went from 3 points to 5 points, right? If you talk about intervals, I had one big chunk. Now I have 2 intervals. Remember, Simpson always has a midpoint. So there are midpoints in these as well. But anyway, I just split it up into half plus half. OK, maybe a figure is needed. So the first one I did said do Simpson on this. And as you know, we just have 3 points for doing that. So that's the first Simpson, right? And it's just one interval. And this is the h for that interval. And then we split it in 2, which essentially just means that you divided h by 2. And of course, you have corresponding midpoints there as well. All right? And the key thing here is what happens to the error. Sorry, it got a little cramped here. But I copied exactly that. But I divided by 16. And it might not be completely clear, but it's a little confusing. The reason is that, remember, you cannot just, you would think this is an h5. But you cannot just, so that would give you, that would tell you that this is half the size of the interval. I would divide by 32. But basically, no, because I'm adding 2 of them. OK? But more easily, you just use the expression that we had before that told us that composite Simpson really scales like h to the 4. It's on the slides right now. So composite Simpson is h to the 4, which means that if you divide h by 2, the error term goes down by 16. There is the h2 for composite trapezoid, and there is the h4 for Simpson, right? So that really just tells you that, this is really just doing composite Simpson with half the h, which means that the error goes down by a factor of 4. Whatever way you want to use to convince yourself that the error went down by a factor of 16. Is that exactly true? It's only true as h is very small. But what I've written is exact because there are different mu's here. OK? So you see the difference? To say that the error exactly goes down by 16 is not true. That's going to be more and more true as h gets smaller. But it's not quite true because the mu is changing. OK? So it is just to the leading order. Anyway, that's not the most important thing. The important thing is, what can you do with this data? You're trying to estimate an integral. This is the same thing, right? We're trying to estimate the integral. And we have 2 estimates of it with error terms. You see that I kind of have an equation out of this? In fact, this here, I mean, the bad Simpson is not as good as the good Simpson. But I'm told that the errors are differing by a factor of 16, which means I should be able to set these equal and solve for the error, basically. OK? And the only issue with that is that I don't know mu, so it's not going to be perfect. The big assumption I'm going to make is that these mu's are the same. And that's wrong, but you've got to do a big assumption. We're completely lost when it comes to fourth derivatives with mu's and mu tildes. So we're just going to assume something to get rid of them, and namely that they are the same. It will, of course, get better and better, because when you zoom in and h gets small, these mu's get closer and closer to each other. So at some point, this is reasonable to do. But at an early point, it's not. In fact, will this be a bound? No. This will not be a strict anything. It could be arbitrarily bad, these errors. But it's practical. So anyway, so what we do next is assume that this fourth derivative of mu is equal to, or I guess approximately equal to that fourth derivative of mu tilde, right? It's not true, and we're going to get the wrong result, but it's an approximation. Then you just set these equal. So you say that the big one divided by 90 f4 at mu is equal to these smaller ones added up plus its error term, which was 1/16 of the previous one. And the trick to make this manageable is to remove the twiddle from the mu. Otherwise, I have no chance. So it's wrong, but anyway. Now you can see what I can do here, because these are numbers you compute, which means that you can solve for the error. Or in other words, you can solve for this h5 over 90 times h times the fourth derivative of f at mu as, if you solve here, you get 16/15 of the difference here. Should have a better notation for this. But Anyway, here's a number you computed. You just move these two other numbers you computed over to that side and divide, and you get this expression, right? And of course, let's go all the way and just estimate the error. So let's say we want to estimate the error in the accurate one, which is really what we just solved for divided by 16. So the 16th goes away. It's really just a simple thing easy thing to remember. It's 1/15 of the difference of the two. Isn't that nice? That's how simple the whole expression is. By error now, of course, which one do I mean? I divided by 16. I mean the accurate one. Remember, I computed two Simpsons. This one and this one. I'm estimating the error in the more accurate one by dividing by 16, right? Of course. Why wouldn't I want to use the more accurate one that I computed? But that's how it works. It's extraordinarily simple. You just have to run Simpson twice, and you can use this trick we discussed to make it efficient. But just to keep it simple, you run it with an h, and then you run it with half the h. You subtract them and divide by 15. And as h gets smaller, this is actually a reasonable error estimate. It's wrong. It's not a bound. It will be too low sometimes. You have to use it with caution. But in order to do the thing that we set out to do, namely just decide roughly that the nuclear reactor is blowing up and we need a small h, this is going to work fine. So that's the idea. Let me show you an example. Let's start here. So what did I do here? Of course, I am doing my favorite e to the x dx. Eventually, I'd like to have n equals 2 and h equals 2. Well, this is the coarse one. So Simpson from 0 to 4. This is just one big chunk for the whole function. It's not going to be very accurate. But anyway, that's, of course, just this, right? And we can compute the number. The h was 2. So this is 1 plus 4e squared plus e to the 4. And it's about 56.76. Way too many digits here because it's wrong. But anyway, that's what you get if you run Simpson on that integral, Simpson's rule. What if you divide h by 2 and you do composite? Well, that's the same thing as doing Simpson like this. You realize that this is composite, where I split it by 2, right? And of course, you can use your 1, 4, 2, 4, 2 for 1 trick here. So this is going to be an h, and I'm going to call it h2, because now I divided h by 2. So this h2 is actually 1 instead of 2. So you have to keep track of that. And what is the expression? The expression is 1 times that guy plus 4 times that guy, 2 times that guy, 4 times that guy, 1 times the last guy. Right? That is composite Simpson. And you can just do this quite easily. Now h2 is just 1, as I said. That's maybe what you have to be careful with. But you just get numbers out of this. 2h squared. I hope you appreciate how easy it is to use composite Simpson here. You can just write it as you go almost. And using a calculator, you get 53.8638. All right? You could look at these numbers and just say, look, I mean, your first instinct might be that you're a little bit happy. Because if these numbers were way off, it would be troublesome. But they're reasonably close. I would say probably not close enough for you to be happy. I would probably refine h by 2, since it doesn't cost much. But here's the question. Just looking at those numbers, you don't really know approximately what the error is. Maybe you would guess that these are pretty close to each other. Let's say the difference is probably the error. And that turns out to be very accurately the case for that guy. But for this guy, it's actually too pessimistic. Because you're allowed to kind of divide, assuming the assumptions we made, you can divide it by quite a factor. So we can do better in estimating this error. To say that the error here is 3 or whatever, the difference, is too pessimistic. the estimated error is really 1/15 of, let me just say the difference, of the two, which is 0.1937. Okay? So he's telling you that it's kind of counterintuitive, I think, that you have two numbers. You're refined by 2. You think you're 3 away, right? Because they vary a bit. But no, you're actually pretty close if these assumptions are true. Of course, we're going to confirm it by looking at the true error, which is, no, true value, sorry. Now you appreciate my simple expressions here, because 0 to 4 of EX, I'm sure we've done this before. It's e to the 4 minus 1. So it's really 53.5982. Seems like this guy dividing by 15 was a reasonable thing to do, but it actually is a little too optimistic, because the true error is 0.2657. So this is probably the first time where my estimated error is smaller, because everything we've done before, I think, has been bounding the error, right? It's a proof. Now it's not. There's some iffiness that I mean, you can put some signs into this, but basically that big assumption means that you don't really know what's going on. You just know that eventually, as it gets smaller, it will get better. But you have to appreciate the simplicity. I did not know the fourth derivative of f. I did not bound any functions. It was the simplest thing in the world. I just did it twice and subtracted and divided by 15, and I got a pretty good estimate, right? And whether that's a factor of 50% or 2 or even 10 of, it doesn't really, it's just so simple. So you use it with some errors of margin, some margins of error, sorry, and that's how this method is working. Let's see if I have something important to add in the slides. You could, of course, do this for almost any method. The trick is so simple. But here's the summary. It's basically what I just drew, saying that 15, it derives the formula at the end, and you might want to take an absolute value. I did not do that. I guess I was lucky that this difference ended up being positive in the first place. Typically, you want to put absolute values on errors. You don't have to. You could say that the error is negative, but you're interested in the magnitude of the error. Now, how do you use this? How do you do the thing I told you before? You have a big, complicated function that varies, and an excellent programming assignment would be for you guys to write this, but I'm not quite doing that. I don't know. It's too few programming assignments. Next time I teach it, I'm going to make 6 instead of 4 or something. It's really important and nice. There are so many nice projects. But basically, what I would ask you to do is to compute an integral from a to b, and you would be able to do this trick of saying that here I can use a big H, but here I need to zoom in. And it's actually not that difficult. It would be a pretty short MATLAB code if you do it well, where you would use these estimates to decide, hey, I don't trust this region, so let's split H by 2 here. Having said that, it's a little bit messy. But let me discuss exactly how you would do it. Here's an algorithm for computing an integral. And of course, what is the user telling you? If we look at the functions we've done before, the input from the user is typically h or n, right? If you want to make composite Simpson, did I do composite Simpson into a function? I don't think so. But we did Romberg. Okay? So before we did this, the reasonable inputs to a function that computes an integral would be the function to integrate, the endpoints, and the number of intervals, right? You see what I mean? The user has to decide on n or h, which is a big, I mean, the user might not know, right? This might not be the way to do it. But anyway, that's all we could do back then because we didn't know anything. If you think about it, what does the user want to say? If you were to use this function and you would like to say, I like it to be accurate to 3 digits, right? You'd like to give it tolerance. So let's say we do that instead. So you're saying that I want epsilon equals to 10 to the minus 3. And here's the algorithm. Well, you run Simpson's rule. You have to do it on the big interval and dividing h by 2. Right? You estimate this error, which we did here. And I guess I multiplied up the 15 here and said, if this number that we estimated is less than, so let's say you give me 10 to the minus 3. This is, of course, much more than that. So I would not be happy. I would keep on going, right? That's how simple it is. You just look at this number and say, is it accurate enough? And it's not. So then here's the trick that now you go into each of these subintervals. Basically, you split the intervals in two. But what could happen is that one of these subintervals say that I'm fine now, I'm accurate enough, and you don't split it any longer, but the other one you would split. And coding this up in MATLAB requires a little bit of care, but it's not that difficult. I'm just going to show you a demo. I showed it last time as well. That gives you. This is not. This is just I ran these functions in MATLAB before, and I think I did a bigger plot, didn't I? This shows what the typical result might be when you do that. I don't know exactly which method was used here, but you can see that it's a function that does almost nothing. We can look at the function. Here's the function. So you see the e to the minus x squared is really killing everything when you get far away, right? So this function is going to be very close to 0 and smooth and nice far away. And then in the middle, something is happening, OK? And here I'm actually using a MATLAB function to compute the integral because I didn't want to code it up. But if you look at it, indeed, far away, the function is not doing anything much. And this method somehow figured out that putting 1 point there and 1 there, and it's, I know it doesn't look like Simpson. There might be a point in the middle, or it's a Romberg. Maybe it's a different method. But that's not the important part. It decided that it's enough to have 1 point there and 1 there and 1 there to get 10 to the minus 6 of accuracy with this method. Because that's what I asked for, I think. Yeah, I asked for 10 to the minus 6, right? So that's quite amazing. This method estimated that these points here are enough to give me that accuracy. Isn't that amazing? It's really not wasting. If you did equal h here, you would have to waste a lot of points here that would do no good. Okay? But then over here, of course, it seems like it's putting them really close together. These points here are really close together. Otherwise, it can't get that accurate. And this is adaptive integration, adaptive quadrature. And this is one example showing you can make up extreme example. For some functions, it's not worth doing. You need to have functions that are smooth and nice in one region and crazy in another. And if not, so you need to know approximately when doing this. Having said that, functions like quad in MATLAB, so all this is implemented. I don't know exactly which method quad is using. We could read the documentation. But there are functions in MATLAB that do this for you. So it's actually quite easy. You just type quad, and it prints a bunch of output, and here is the value of the integral, right? This is how you want this to work in a final software. F, left endpoint, right endpoint, tolerance, and the one, I don't know what it is. Trace. It shows that it outputs all the stuff it's doing. Probably you don't want to see that. You just want the number, right? And this number is more or less, it's not guaranteed. There are no bounds here, but it's kind of making sure this is accurate. So the simplicity is kind of nice. And I know what you're wondering, why are we even learning how to do this? Can't this be used as a black box? And the answer is that a huge community can actually use numerical methods as a black box. People who use Excel for financial stuff or for any just simple estimation, they don't need to know about the IEEE standard and cancellation. But scientists usually go a little bit beyond that. This quadrature has limitations. I mean, students come all the time and say, I'm running MATLAB and it takes 2 years to finish. What should I do, right? That's when you need to know a little bit what's going on, because there are big limitations here. But anyway, seen from this perspective, it's of course quite easy. All right, so we're not going to code up the adaptive quadrature, but you have some exercises on it. Typical exercises are based on similar things that I did, namely estimating the error, and of course knowing the idea that you could do this refinement with it. All right? I was supposed to do this last week, so now I've caught up. So here comes a nice new topic, Gaussian quadrature. I don't know if you've seen it. It's actually one of the more, well, there are a lot of beautiful topics, but it's really nice. Little neat trick to do this. And here's how I'd like to start by saying why there's a need. So Gaussian, because Gauss did it first, I guess. Quadrature, because as I told you, that's a synonym of integration numerically. Think about the midpoint method. Consider the midpoint method on the interval. I'm going to go to -1 to 1 because it's convenient. I think I convinced you guys that we can move things around. I'll give you more explicit expressions later. But I did say already last time that you can certainly move any integral, move the whole function and everything down to be centered at 0, and it's the same value of the integral, right? And I'm making another thing now. Suppose you want to integrate a width of anything. You can always divide by that and make it a different width. This is a normalization that are just based on trivial properties of an integral, namely that if you move it to the left and the bounds, nothing happens. And if you multiply the x by, there's a product, there's a factor that comes out. We'll do this later. For now, just accept that it's enough to know how to integrate from -1 to 1. If you know how to integrate from -1 to 1, you can just integrate from any a to b easily. All right, so here's a function, f of x. And the midpoint method, what does it do? It puts one midpoint and replaces by a degree 0 polynomial, right? By the way, this is an open coats formula in general. Namely, you spread out points, and you skip the boundary point. In this case, you spread out 3 points, but you skip the boundary points. It's just 1 point. But it's easier than that. I mean, in calculus, we just say immediately that clearly the integral is approximately the width, which is 2 times the midpoint. Right? So that's the midpoint method. Remember degree of precision? What is the degree of precision of the midpoint method? It's the polynomial that is most accurate. Clearly, it's perfect for a constant, right? You shouldn't think twice about that. I evaluate it in the middle and multiply by. If it was a constant, it would, of course, be perfect. But there's a little bit of magic here, namely that it's actually going to be perfect for x as well. So the way to see that is the following. If you integrate from -1 to 1 a constant, or 1, you get 2. But if you do 2 times f0, you also get 2. So I say check. I verified that the rule is perfect for a constant. OK? For the next one, you look at, let's do it over here. You do integral from -1 to 1 of x. And you realize that's actually 0. And your rule would say 2 of f0, which is 0. So it's actually a check on that one too, right? So now I've proven that the degree of precision of this method is at least 1. Have I shown that it's equal to 1? Hint is that I said at least. If I really ask you, if you answer, I mean, strictly speaking, if you answer it's equal to 1 now, that's not necessarily true. It's the highest. So you got to do one more. So this is something else, right? This is x 3/3 from -1 to 1. This is 2/3. But your rule would still say 0. So that didn't work. So in degree of precision is really equal to 1. Anyway, don't be too depressed about that. It's kind of amazing that it seemed like we got 1 degree for free. By the way, I'm testing this with a constant and x. You might think, and you should think, that, wow, does that really mean it's perfect for any polynomial of degree 1? And you could think about it and realize, yes, because of linearity. Namely that if you add these two, if these two are perfect, and you add them, that's going to be perfect. What if you multiply any of them by a number? That's also linear in the sense that integrals just scale. If you multiply this by 10, everything is times 10, including this number, right? So yeah, it is kind of amazing. You just have to check 1 and x. And you know that it's going to be true for any combination, linear combination of them. It was not perfect for this guy, though. But let's look at the trapezoidal rule. Trapezoidal rule uses 2 points. But it's still only precision 1. How do you check that? Well, you could do the same thing again. Let me just do it. It's clearly, trapezoidal rule is clearly perfect for the, remember the trapezoidal rule said h½ times f left plus f right. So for a constant, the h is equal to 2 and all the f's are 1, right? If you set it to 1. So that's equal to 2, I guess. So yeah, the constant works out fine for the trapezoidal rule. The linear, this should not be a big surprise that it works out perfect, because the trapezoidal rule is really drawing a straight line. And if it was a straight line, you'll be perfect, right? But let's just check it. So it's h half times, let me just do it immediately. So now it's going to be minus 1 plus 1. So that's 0. So that's also good, right? But as I said, we don't know if it's more before we check the x square. So fx squared gives us 2 over 2 of 1 plus 1, I guess, with trapezoidal. If you integrate x squared with trapezoidal, you get this number. And that's also 2, which is not equal to what it's supposed to be, 2/3. So that didn't work, right? So the degree of precision is 1 there as well. And you might say, what's the big deal about that? Well, it is a big deal because it uses 2 points. Which would, if this was all you were doing, which method would you obviously choose? Remember, trapezoid did this. But, you know, I mean, sometimes it's bad that computers are so easy to use, because you don't really see the issue. But if you were doing these f evaluations by hand, but even if, suppose you're doing billions of them in a computer, right? It seems like midpoint method would be twice as fast, assuming you spend all the time in these f evaluations. So, you know, and that's really the case. But here's the next question. What happened with the midpoint method? What is it that gave us this extra degree? It's because we evaluated right at 0. It was some symmetry thing going on. Suppose you do midpoint method. Here's a stupid midpoint method, where I put the point a little bit off. And I take that value and put one there, right? I mean, that's actually working. It's a convergent method. But then you lose that. Then it's just degree of precision 0. Easily to check, because you don't get the nice symmetry, though, with a 0. So there was something magical about putting the point at 0, based on symmetry. And there's symmetry in trapezoidal as well, minus 1 and 1. That's symmetry, right? But apparently it didn't give us the same magic. So Gaussian integration or Gaussian quadrature, ask yourself, can you do better? Let's say we use 2 points. Can we choose x1 and x2 to get a better scheme? And by the way, I know some people ask about these words. Method, scheme, computational scheme. Yeah, there are a lot of synonyms. Scheme is really a numerical method, or a numerical recipe for computing something. How would you approach this question if I gave it to you? It's not. I mean, there's going to be magic soon. Something called Legendre polynomial. That is, it's just beautiful, but it's not intuitive. Let's first do the completely obvious thing of just trying to do it. Okay? And by that I mean, remember trapezoidal rule? Put points as minus 1 and 1, right? Let's see if we can put them somewhere else and see what happens. This is completely straightforward. I'm just going to try. So I'm just going to say, suppose that you are going to have a rule of the form we always do. Namely, we're going to have a point, and I'm going to rename them x1 and x2. But really, this is what we're doing, right? We used to call them 0 and 1, but for Gaussian quadrature, it's sometimes easier to just start at 1. So you evaluate f at 2 points, and you multiply by numbers. Trapezoidal rule is doing this with minus 1, 1, and weights h half, right? So that was OK, but maybe we can do better. What do you think is going to happen if you just think of accounting equations here? How many unknowns did I have? How many things do I have to play with in my method? I have these 2 constants that we already chose well for trapezoidal. But you can also play with these 2 numbers. Sounds like I have 4 numbers to play with. And if we're lucky here, it sounds like we might be able to actually kill off all the way up to degree of precision 3. And that's a little bit of magic. Why would we be able to just move the points a little bit? So basically what I'm trying to do here is to find new points. This picture is getting messy, blue. I'm going to find new points such that with appropriate weights, and actually you could draw a straight line, but I'm not even going to draw the straight line because I didn't really assume it. Okay? I'm just saying there are things you can multiply these two numbers by, so you get fundamentally much better than just doing the endpoint. In the same way as this midpoint here for the midpoint method was fundamentally better than any other choice, right? So, and doing it, the algebra is obvious. But my argument here is that we have 4 coefficients. This could, well, it's nonlinear, so it's not clear, but it could be accurate to degree of precision 3. Okay? And it will. And let's see how to do it. So this is, by the way, an alternative way to derive. This whole degree of precision is an alternative way to derive these schemes. You just do it like we did it. Okay? So I'm claiming that the true integral is equal to 2. We did it before. The true integral is equal to 2. And when you plug it into your method, it better gives the same result, which is C1 times 1, right? Plus C2 times 1, which is C1 plus C2, OK? What does that mean? If C1 plus C2 is not equal to 2, you will not even integrate the constant right. In other words, you better make that happen. Trapezoidal method does that. Remember, h was 2, so that's really what trapezoidal method does. But let's keep on going. Then you set it to x, and we realize the true integral was 0. But your method will give you -1 plus 1, which is really C2 minus C1. Of course. What did I write? Sorry. That went too fast. I'm not plugging in. This is not trapezoidal method. So my rule now, what happens if you use your rule on the function f of x equal to x? It's going to take C1 times the function at x1. That's minus x1. Because the function is just x. No, sorry, that's really minus. I'm thinking symmetry. We'll come to that later. It's really just x1. It's C1 x1. Why? Because f of x is x. So f of x1 is equal to x1 plus C2 x2. OK? I don't know what this is yet. We'll figure it out in a bit. But given that you have all these 4 numbers to play with, this is the number that comes out. You better make sure this is equal to 0. But then we said we can probably keep on going. So we can go do the x squared. This was 2/3, right? And what will your method do to it? It will do x1 squared and x2 squared. And you know, we were greedy. We thought we could do even better. What is the true integral for x3? 0. All these anti-symmetric ones will be there. And you know, if you believe what you were taught in high school, namely that same number of n unknowns and equations, you should be able to solve it. That's of course not true, because it's nonlinear. But it works out in this case. Then we should be able to do this. Just for monitoring purposes, this we have no hope of satisfying, but who knows? It's nonlinear. Maybe we're lucky, right? And I think it ends up being 2/5 equals C1 x1 to the 4 plus C2 x2 to the 4. All right? We don't think that's going to happen. But I'm hoping to put check marks on the 4 first of them, right? And how do you solve that? Well, I don't think we're not really trained for any type of techniques for solving nonlinear systems of equations. I think every time you've seen this in math courses, you just guess around a little bit, right? There are more or less systematic approaches. Of course, the right way to do it is a numerical method for systems of equations, but that's 128b material. So let me just cheat a little bit to make it easier. Assume symmetry. So I'm going to say that I think these c's are equal. And I think x1 is really negative of x2. Okay? So all I said is that on the left and on the right, these are going to look the same. That's OK. I could find a solution. But nonlinear, there could be other solutions. But there's not. But then it's easy to figure out. Because then equation 1 gives us everything falls in place when you do this. So this is equation 1, 2, 3, 4, 5. Then equation 1 gives you that 2 is equal to C1 plus C1, or C1 is equal to 1. Is equal to C2, by the way. So that was easy. 2, 4. Since I assume symmetry, you see they fall in place automatically when we get these C's equal. Satisfied? And it remains to choose the magic number x1 equals negative x2. And that's, of course, equation number 3 that gives us some information of that. Namely that 2/3 have to be equal to x1 square. And then it's really plus x1 square, right? Because I assume symmetry. And the minus signs go away. That's 2x1 square. Or x1 is equal to plus minus 1 over square root of 3. And of course, because we assume symmetry, let's just say that x1 is negative 1 over square root of 3, and x2 is positive 1 over square root of 3. Now we have everything. And it will satisfy these equations. But you know, whatever I did here is kind of a trick, right? The important thing is that it seemed to work out. What is my degree of precision? 3, at least 3. We don't know. Do you know that it's 3 exactly? You might want to check the last one. But it seems unlikely, but strictly speaking, you could look at number 5 here and say that 2/5 is not equal to 1 times, well, that's going to be 1 square root of 3 to the power of 4, right? That's not satisfied. So degree of precision is equal to 3. It's a nice method. You can really write it like this. 1/1 of fx dx is approximately equal to f of minus 1 over square root of 3 plus f of plus 1 over square root of 3. Isn't that a neat short formula? And it's extremely much more accurate than, in fact, it's accurate like Simpson's method, almost. Let's see, the first one, that's Simpson. Remember, it has a 4th derivative, right? So the degree of precision of Simpson's method was also 3, although there's a different error constant, but that's OK. Anyway, we're greedy. We want to keep on going. What else can you do about this? And there's a nice piece of math here. Let's see. Yeah, we be able to start on it at least. But this is the idea. And one way to understand it is really just to say that this is all we need, right? The problem is, of course, that it was a little iffy when I solved these. And you can imagine what I want to do next. I want to come up with a bunch of these methods that are more and more accurate. So imagine that I go up to 3 points. And by the way, they're going to be symmetric. It can be shown that they're symmetric. But we want to be able to do things like this, where you have a function. And these two points, can't we put 3 or 4 or 5, any number of magic, specially chosen points? For example, 1, 2, 3, 4, 5, such that you could make this extremely accurate. And if you're lucky, you can at least dream a little bit about what accuracy you might get. Because remember, if I'd used 2 points, I had 4 coefficients. And I was hoping that would give me a degree of precision 3, which it did, right? Which means that if I put out 5 points, in principle, at least I will have 10 coefficients, right? Namely, what I multiply them both and the location of these points. Sounds like I might be able to be accurate up to degrees of precision 9 with just 5 points. It's a huge. But the end result here is a factor of 2. But it's a, and that maybe is not so exciting, but it's actually just fundamentally much better than the other ones. It's going to be that factor of 2 that pops out. You do 5 evaluations, and you're getting this accuracy out of it. All right, so let's do it. So in order to derive these, you can imagine having then 10 equations, even with symmetry. I'm sure you could solve it, but it becomes a little bit of a mess. So let's see if we can do it better. And then you learn some nice math in the meantime on orthogonal polynomials. So Legendre polynomials. Have you seen those? They are defined as follows. And it's not at all clear why I start talking about this now. But it will lead to a nice little theorem that gives you all of these quadrature formulas. So let's say these are special polynomials that we call Pn of x. Not at all a clear notation what this means. You have to understand from the context, because we call a lot of things Pn. I think we call the Taylor polynomial of degree n. So be careful with notation here. It's defined to be, let's say, a monic polynomial. Monic is not interesting. It just means that the highest coefficient is 1 of degree n such that, and here's the property of these polynomials. If you integrate any other polynomial times this polynomial, you get 0 if that polynomial has less degree than n. Okay, so you can define them completely by this. You have to prove that that it can be done and that they're unique, etc. But this is what you want to do. So you know, I'm asking for polynomials of, let's say, degree n is equal to 5, such that if you integrate it times 1, it's equal to 0. If you integrate it times x squared, times x3, times x4, they're all equal to 0. Can that be done? Yes. And I'm not going to, there are actually nice, really short and nice ways to get them out. Let me just list them here and say that the 0th version of this is just a constant 1. You can't really test this condition for that equation, because I said that you integrate this guy against everything with lower degree, and it should integrate to 0. There is nothing lower than 0. So this is kind of well specified without the condition, right? The next guy is going to be p of 1 equals to x. Okay? So what does it say? Well, it's a polynomial of degree 1 with leading coefficient 1. If you integrate this against anything with lower degree, from 0 to 1, you're getting 0 out. Not a big surprise. Multiplying by a constant, and it integrates to 0, right? It will get interesting now when you look at the next guy, which is x squared. So this is less trivial. That here we have an x squared minus a third, but you could indeed check that it integrates, multiply it by any degree 0 polynomial and integrate, and it's 0. But also multiplying it by any degree 1 polynomial and integrate, and it's equal to 0. Okay? And you can keep on going. One more. P3 is equal to x cubed, then it's minus 3/5 times x. Anyway, so fun little exercise is to do those integrals. You realize that's completely trivial. It's just monomials. So if you wanted to check that this times x integrates to 0, it's really x cubed, which you integrate a primitive function x4 over 4. It's really easy to check. I'm just not going to do it. Here's why I like these. Here's the nice theorem. And the theorem is Gaussian quadrature. And we'll look through it much more. Right now it will seem a little weird. So here's the punchline. What is the 0? What is the root of P1? That's right at the origin, right? X equals 0. That was the point for the midpoint method. What are the roots of this equation? It's x equal plus minus 1 over square root of 3, right? Hey, those are the points we had there. All right, that's going to be true in general. So the roots of these are those magical numbers. And we'll see why. It's not that complicated. But basically, choose x1, x2, all the way up to xn as the roots of Pn. And then you got to do this coefficient, and this is not so interesting, but it has to be there. But I'll show you why these numbers come out later. Minus xj. You got to choose the coefficients as well. And this comes from the Lagrange polynomial. So I'm saying what these coefficients are, but this is the general Gauss rule of n points. So the theorem is telling you that then, if you integrate any polynomial of degree, I'll tell you what the degree can be. For all these points, if degree of p is less than, I'll let you think a little bit about this. All right, let's start here. I want to compute an integral from -1 to 1. I call it p instead of f. You're going to use it with an f, namely any function. But in my theorem, I'd like to say that it's exact for polynomials. So I'm saying that it's equal to this, if this is a polynomial of high enough degree, or low enough degree, I guess. What is this? This is the same thing, right? You want to integrate the function. You have these numbers, weights, c, and you evaluate the function at magic points xi. I'm just adding them up. It's just generalized. I'm telling you here that these points are given here and the weights. And what degree of polynomial do we hope to be exact for? It's what I said before. If we're lucky here, it sounds like we have 2n coefficients. And that means we should be able to integrate exactly the polynomial of degree 2n minus 1 and below. So strictly less than 2n is what it gives. And this is the theorem. And it's really true. And I'm going to show you why, because it's kind of neat how it works out. So let me just say that the c's are not that interesting, but they're needed, of course, but they're not super interesting. Why? Can you all see that the big problem when I solved this was the x's? In what sense do I mean that? All the c's appear linearly. So the x's are the trouble parts with all these squares and cubes and everything, right? If I give you the x, finding c is really easy. It's a linear system of equations. So in principle, from a practical point of view, and this is, I think, how I do it in my MATLAB code, you can just solve for the c's. It's not difficult. Now, that particular c comes from just integrating the Lagrange polynomial, which we'll do in the proof. But I know it looks messy, but the Gaussian quadrature is almost easier to describe. The x's come for the roots of these polynomials, and the c's are whatever they need to be to satisfy those equations. But anyway, let's see what's happening. So we split it into two parts. First, we consider that the degree of polynomial is less than n, strictly less than n. That's the easy part. Remember, even trapezoidal rule was satisfying this, right? So this is what I would say the not so magic part. And the magic part is going to be when we later say that, well, you can go all the way up to 2n, not inclusive. So what we do here is just to say, put a Lagrange polynomial through those points. And I'm going to say px is equal to sum from 1 to n of p of xi times these l's. And remember, I don't even indicate the degree of those l's because it's understood. And that's going to be sum from 1 to n of these numbers, x minus xj over xi minus xj times p of xi. OK? Why am I saying this, by the way? How can I say that the polynomial is equal to sum of the same polynomial evaluated at points times L? Because that's, I think we have that as a theorem a long time ago, that any polynomial of degree n is uniquely given by its n point, of degree less than n, is uniquely given by its n points, right? So given that we assume that it's a polynomial of degree less than n, this is going to be the case. And that's just a good old Lagrange. that you should have seen before. I'm just integrating it. Anyway, now let's integrate it. So the integrating this p is equal to, remember how we started deriving the trapezoidal rule in Simpson? You gave me the points, I put the Lagrange polynomial, and I integrate it. It's exactly what I'm doing. So this is exactly what we did before, and it's not that extra Gaussian magic. That's going to come later. And what you do is that you take this big sum of product not I, x minus xj, xi minus xj, p of xi, and you integrate it. And when you do that, this method pops out as it is. Namely, I'm going to just flip the order. So we take out the sum here. And inside here, we get the integral of the product. Let's see, j not equal to I of x minus xj over xi minus xj. It's the same I'm writing over and over, dx. And then we end and multiply by p of xi. OK? Oops. So you saw what I did? I just popped out. This is why those CIs are chosen in that way. Because if you do, I'm going to have to switch to this thick chalk. Then you get really what we want, namely CIs multiplying P's of xi's. All right? And again, I'm emphasizing this is exactly what we did back in 4.3. When we derived trapezoid and Simpson and any closed or open Newton-Cotes formula. You just tell me any n points, and I'm going to put the polynomial through them, and I'm going to write it in this annoying Lagrange form, because it's an explicit form, that I can integrate and get actual expressions out. This tells you why the c's must be equal to this. Right? This you could do for any points. As long as they're not the same, as long as they're distinct, you could play this game for any points. And indeed, trapezoidal rule does this with 2 particular points, right? So let's now do the next part that is more interesting. Next, suppose that the degree here is. So what is special about these points is that they will actually be exact for this class of polynomials as well. And here comes a little bit of some nice tricks. You start by dividing by Pn. Okay? Remember, Pn is the Legendre polynomial with special properties. You all know that you can write it as a polynomial as a q, a quotient, times what you divided by, plus a remainder. All right? Long division. We're not actually going to do it. We're just proving a theorem. When you're done, you will never be dividing polynomials. It will just work out. But in order to prove it, you know from high school that if you give me a polynomial of this degree, you can divide it by a polynomial of degree n and get another polynomial, quotient. But in general, you get a remainder, right? Of course, if you luckily divide it by a factor, the remainder is 0. But that's not so interesting. Or in other words, didn't we do this with Horner? So, dividing can always be done. The reason we do this in the proof is that some nice things will happen here. Just pointing out here that the degree of the quotient is less than n, and so is degree of the remainder. Right? And let's see how that helps us. Now basically just plug in. I want this one. So I'm just going to, and I want the theorem. All right. This is the only blackboard left. Oops. So let's see what happens now. All right. So let's see. The method plugs in xi, right? What will the method do? Q of xi times p n of xi plus r of xi. So when you use this method up there, the Gaussian quadrature, it's actually going to do this. Okay? It's equivalent. P of x is equal to that. You're not going to do it in practice. You're going to do p of xi. but that's equal to this expression, which is equal to what? Here comes the magic, which shows the point to kill off this term. Okay? If you choose trapezoidal rule, that's not going to happen. Then it's something else. But anyway, we did. This is just R of xi because of how we chose the points. All right, and then we look at the integral from -1 to 1 of px. And we can again use our new form here, which has a q times the Legendre plus a remainder. What is this equal to? Remember the other special property of these Legendre, multiplying by anything of a lower degree, and it integrates to 0. Right? So this is really just the integral of R. By that property. Okay? But the degree of R is less than n. So the integral of R is equal to the quadrature rule applied on those points. And that's all you need to know. All right, let's go through it again what happened here. You're actually going to use the formula as it is, namely you're going to compute an integral of p by just evaluating p at these magic points and multiplying by weights and adding. This is how you use it, okay? I'm just proving now that it's an awesome formula. First of all, it's great for polynomials up to degree n-1 because of trivial things. We've done that before. But now, if it's between n and 2n-1, you divide it away, okay? Just to get an equivalent. Every time it says px, we can see it as being this, right? And that creates two effects. One is that when you plug in the points xi, you're actually really just evaluating the remainder. You don't see this big product of the quotient and the Legendre, because I chose the points to avoid them. So I'm really just getting the remainder at xi. Now, if you integrate it, you can really just write this integral as the integral of the remainder, because of the special property of the Pn. Okay? But of course, you're computing this, which was equal to that. You're adding those up, right? So you're really just evaluating the integral of R, and they are equal, so therefore the formula is perfect. It's kind of a magical in that sense. It's the best you can do. You can prove that it's the best you can do. But, well, yeah, I might have to think about it. I wrote a function. Let's look at the function I wrote. It might make you happier. So, of course, I mentioned already that you could easily get our rule out by just solving for roots here. What if you want 3 points? Sounds like the points are going to be x equal to 0 and plus minus square root of 3/5. And then you solve for the c's. So it's very easy to come up with these. I do have a general formula, though, in a formula called in a function called Gauss quad. There are a few issues with this function. I'll discuss it later. But basically, I'm setting up Legendre polynomials, and you don't need to know how to do that. But I told you before that there's a way to produce all these guys. Okay? Just Wikipedia it, and you can see it in a beautiful little, you see 3 lines of MATLAB, or 4. I produced these polynomials. I think I showed you before the command roots. It finds the roots of a polynomial. I'm sorting them just because I want to, because roots doesn't give them sorted. Okay? And then I have a different technique that I can show you later, but because I don't want to do that messy formula for the c's, I don't want to compute those integrals. So I'm actually doing the thing I mentioned before of solving a linear system. And we can see where that comes from. But let me run the function. If you do Gauss quad of 1 point, it gives me the point 0 and the weight 2. In other words, the midpoint method, right? Good. And the way to see it is, of course, that it's the 0 of this function, and the weight is whatever it wants to be. Now let's do 2 points. What are these numbers? That's the one we did on the blackboard. That is plus minus square root of 1 minus over square root of 3. And there you have weights of 1. We derived that before. But you can keep on going. And I guess these points are now 0 and plus minus square root of 3/5. And the c's are whatever they want to be. And you can compute them, right? All right, let me show you how accurate this can be. What are we integrating? F, always this one, right, from 0 to 4. So what I'm saying is that the midpoint method, midpoint, I'm just commenting here, midpoint would say that you do f at 2 times the width of 4. OK? That's not so good. True integral equals this, right? So that's horrible. Midpoint is just not doing a good job there. Let's do Gaussian n equal to 2, right? Then you compute these points. I need format compact here. It throws away all my accuracy here. So how do we use this formula? I didn't quite show you how to scale it yet. So why don't I just move it back down to -1 and 1? So let's do that instead. All right? So midpoint is going to give me midpoint times 2, right? There's a number. If you want to integrate e to the x from -1 to 1, you get 2. OK? True value is going to be e to the 1 minus e to the -1. And it's pretty bad, 20% error. Now let's do the first Gaussian quadrature rule. Gaussian n is equal to 1. And then we compute it like that. Sorry, Gaussian n equal to 2, right? There are the 2 points. And what do? We evaluate the function at the points. We multiply by the coefficients, and we sum. Are you all OK with MATLAB in that form? So it's really a sum, right? So if you want to write a for loop, that's fine. But I'm evaluating all the functions at those 2 points, and I dot times the c's. And of course, out comes a better value for this integral. And you can see that it's enormously much better. In fact, if we do minus true integral, the error went down to something very tiny, right? But if you really want to, I mean, this is almost too easy. With 5 points, you get 10 digits of accuracy. So this is used a lot. This is sitting in every finite element software out there. Integrals are very often computed with this Gaussian quadrature. Anyway, I think you know enough for those homeworks at least. And I'll see you on Thursday.